All right, today, folks, we're going to be talking about translations of our parent functions. We just dealt with scale changes for the most part last time, but we're going to start the same way we did last class with sketching the parent functions. It's really important to be able to translate these functions that we know the shapes of the originals. Okay, so what I want you to do to begin here is just grab out a piece of scratch paper, and I want you to make 3 just T-table chart-like things with an X and Y axis. And then you'll notice I've already labeled 4 tick marks each direction, representing the 4 points on the unit circle. Okay, so do the same thing there. And after you've got that, what you're going to do is pause the video and sketch those parent functions from memory and using the unit circle. Okay, we'll go over them before we get started today. Okay, so hopefully your graphs look all right here, and I don't want just a rough sketch. It's really important that I see each of these points in their appropriate locations. And then I just wanted to bring back some of these items from what we did last time. Okay, so domain for a scale change is not going to change anything. Okay, range may be affected by a scale change if we have a vertical stretch or compression, but the parent is -1 to 1. And then both the 2 pi for the period and the amplitude of 1 would be affected by scale changes. If we had a horizontal scale change, that's going to affect the period, and a vertical scale change is going to affect the amplitude. Okay, tangent, I wanted to go ahead and talk about its domain since that's something that looks a little bit messier. Okay, so with me here, let's talk about that. We've got theta as our variable, so I'm going to use that. And we have to just write the restrictions. Okay, so we're listing out the asymptotes because those are the places that we don't have values, or the angles that don't work for tangent. And so we're going to say not equal to and list our first asymptote we see, and that's at pi over 2. And then remember, we just say how often they occur after that, and it's every period. So for us, that on the parent function is pi, and that only works as long as we're taking it times integers. So we've got to add n is an element of the integers at the end. Okay? Recall there is no amplitude for tangent, so a vertical scale change would stretch this out, but it's not going to affect your range because we don't have a maximum or a minimum point. Okay? So what we're going to do for translation today is just kind of like if you were in class, I'm going to have you read through this information, and I want you to attempt all the problems on the front page, so that's 1 through 3. I am going to encourage you to get out your purple note card for translations, especially with what we're doing today, dealing with H and K specifically, but it does have all the transformations, including scale changes from last time. Okay, so grab that out and then work through problems 1 through 3, and you can come back to the video and check your answers. Okay, this one I was just looking in words for left. Remember, it's the opposite of what you see in here. But the rule, this is on your note card. It says x plus h and then y plus k. It's the beefed up version of what you did in Algebra 2, where you just use the hk subscript. We're going to use this to talk about rules. Scale changes had an a in the front and a b in the front on those ones, excuse me, to represent if we were multiplying instead. Okay? This rule and scale change rules both have a direct relationship through the graph, so I want you to add that information there, because that's the biggest thing that's confused, is we get in such a habit of switching this part and using the opposite sign that sometimes we want to do it with the rule as well. But the rule tells us take the x value and subtract from it, which would make things go lower on a number line, which means to the left on the graph. Okay, hopefully you didn't have any trouble with this translation since it just was up 2. Okay, but what might help is looking at that original graph that we drew to start out with and just individually shifting each point. So this first point starts at 0, 0. You can hover on it, and then just this plus 2 means go up 2 from there to plot your first point. Okay, then this point starts here normally, went up 2. Okay, what I like to do instead is only use the translation for the first point, and then use the pattern after that. So the pattern, we go up, whatever the amplitude is, 1 for us. Then we go back down, but twice. So down and then down again, and then back up. And using that pattern gets us there a little quicker once we know the first point. Now, a vertical shift, we're talking about the things or the features of our parent functions. A vertical shift is only going to affect the range on this graph. It's not going to affect the domain, the amplitude, or the period, because those amplitude and period will only change under a scale change. Okay, hopefully you got true, because translations do not change the size or the shape. If I change this to scale change, it would actually be false, because the size does change under a scale change. Okay, I didn't give you a parent function here, so you could have chosen for the equation, but we'll go through each piece. Amplitude and period stay the same under a translation, but this h value is the phase shift. Now, I want to talk a minute about this word phase shift. Okay, by definition, if we go back here, by definition, a phase shift is the least magnitude. Okay, it could be positive, it could be negative, but it's the smallest size of shift, because there's an infinite amount of translations that could get you to the same graph. I'm going to show you an example of that. Okay, so I picked the parent function sign here. We've got that in red. And then I also picked on just a translation that took that original parent function and moved it to the right, pi over 2. And you can see that here. But what I want to talk about is an identical translation. So I could say that I'm going to the right pi over 2, but what I could also do with this graph is look at another point that matches my beginning feature. So here, my beginning feature is the midline where the graph starts to go up afterwards. So that does occur at pi over 2. But it also occurs over here at negative 3 pi over 2. So if I want to say go to the left 3 pi over 2, I would write y equals sign, and then x plus 3 pi over 2. And you'll notice it graphed right on top of that green curve that I had here. These are equivalent. And they're equivalent because you'll notice the distance between these 2 points, the negative 3 pi over 2 and positive pi over 2, is a distance of 1 period, or 2 pi. So technically, okay, the phase shift is the smallest translation that would get you to the graph, even though there are more than one. So in the case of the ones that I'm going to give you, when I actually ask you to identify the shift, the h value, I'm going to give it to you so it's already the smallest number, almost always. So here, this was 2/3 pi to the left. I could also say go to the right, the same distance, or the distance that would add up to 2 pi. So if I'm at 2/3, I would need 4/3 to get to 2 pi. So I could say this is equivalent to going to the right 4/3, which is a larger distance. So this really is the smaller one. Okay, again, most always I'm just going to give you that smaller version. Okay, and then the equation at the end had the -3 just from that vertical shift. I didn't ask you to identify it, but that would just go downwards 3. Okay, now we're going to graph number 4 together, since this one has a phase shift. Okay, so the first thing we're going to do is identify that. Okay, our phase shift gives direction on the graph. So when we see a plus, that means left, or a negative h value. Okay, and again, that's the phase shift, because going left pi over the 3 is the same as going right 5 pi over 3, which is much larger. And we're going to sketch 2 cycles of the curve. What I'm going to recommend you do for these ones especially is sketch the parent function, so you have something to reference. So the parent function for cosine starts at the maximum. Notice I didn't say starts at 1. I said starts at the maximum. We want to get into the habit of talking about the feature of the graph versus the value on the graph, because that feature doesn't always land on 1 under these transformations. Okay, so we're going to say at the maximum, and then what we're going to do is shift each of these points to the left, and we're going to go left pi over 3. And so that's a little bit of a tricky part here, is when our scale doesn't have pi over 3 on it, We don't want to change our scale, so we see that, because what's really important here is these distances are still pi over 2. So shifting the first one's not going to help us necessarily, because we still have to go a distance of pi over 2. So it's nice to actually keep that scale there, since our period hasn't changed. But what we're going to have to just visualize is where this pi over 3 falls, given our scale. Okay, so what I want you to do is think about this as -1/2, -1, 0, and think of this as -1/3 in terms of our pi. So if we focus just on the fractions in front of pi, we're trying to place -1/3 on a number line. And we know it's between 0 and 1/2, but we want to know which side it's closer to. Okay, so think about the decimal. This -1/2 is -0.5, and -1/3 is -0.3 repeating, so it'll be closer to this 0.5 than it is to 0. Okay, so starting at my first point, okay, so just hovering like normal, we're going to shift it over that little over halfway. Okay, and again, we could do this with each individual point, but I think it's easier just to follow the pattern, knowing that they're going to space out the same distance, meaning now that I know I'm floating to the left side of the box, all of my dots are going to float on the left side of the box as I go around here, and I just have to follow the pattern here. So I'm going down twice and then up twice. Okay, so down twice would be here first on the left side of the box, then down again, left side of the box, and then I go up twice. So up one section to the midline, and then up another section to the maximum, and I'm just staying that same distance, so this between my 2 points is still that pi over 2. And then I just continue this pattern on the other side. And connect them. Okay. Okay, now what I'd like you to do is pause the video again, and you're going to write equations for 5 through 8. Okay, there is more than one way to write an equation for these periodic functions. And when we're talking about the shape of a wave, you can use sine or cosine as the parent function. Okay, we try to use the one that makes our life easier. Okay, so try each of those, and then we'll go over them after you get back. All right, so there were 2 ways to do number 5, and this one was actually the most challenging one. Okay, because the points that they labeled, neither of them correspond to the starting point of sine. Because sine starts at the midline. Okay, remember the feature, not the value. Okay, it starts at the midline where it goes up afterwards. So that is not this -2/3 pi or this +4/3 pi, because both of those go downwards first. Okay, so there are 2 ways to write an equation for this. The first one, if you want to use sine, okay, we can use this point if we say it goes downwards first, and that's a reflection. Okay, this point moved to the left, so we put a +2 pi over 3. Alternatively, we're going to look at the feature where it should start, and that's this point right here. Okay, I'm going to talk about how I got this pi over 3. Okay, we're going to use the points that are labeled and our knowledge about sine, the parent function. We know on the parent function, to complete one full cycle, it takes 2 pi. Okay, and so this point, down, up, and back will take 2 pi. So then we know this distance to the halfway point would be a distance of pi. So what you can do here is take -2/3 pi and add 1 pi to it. So a -2/3 plus 1 is a +1/3. And that puts us as 1/3 pi. But again, we're thinking about translation from the parent function. So the parent function usually starts at 0, 0. We have moved to the right pi over 3. In order to make that work, we say minus pi over 3 in the equation. Okay. This one just went up 2 if we talk about the parent function of sine. I did want to actually have you write this as cosine as well. I am on your homework going to ask you on 2 of the problems to write the graph as both sine and cosine. So being able to look at it both ways is going to be important. So if it's cosine, we're not looking at the feature of the midline, we're looking at the feature of a maximum. Okay, and what we want to do is always go with the one closest to it. So that's this maximum, not this one. Okay, and then we just go see where it's at. So this one hit a nice value of pi over 2. And we went to the right pi over 2 from where it normally is. So we say minus pi over 2. Okay, really important, and we talked about this last time, the midline of the graph is always the k value. Okay, so don't be confused with cosine. This value, I can see the maximum's at 3. The maximum is not the same thing as the shift. The vertical shift is always the midline or the middle of the curve. Okay. Tangent graphs. Okay, so tangent graphs, this one went just to the left pi over 4, so plus. This one had a little bit of a typo there, but to the right pi over 2 here. I will tell you that's actually equivalent on this one to going to the left. Those translations would be equivalent. So you could actually say plus pi over 2 and you'd get the same graph. Both of them are equal distance, so both of them would work out for me. Okay. Next time we're going to put together with scale changes. So it's a good idea to start looking at other features while we're practicing this. Okay. So some other things we want to recognize is the period of the graph, making sure it hasn't changed. Ours is still pi here. Okay, on this one it's less obvious to see. So if I go 0 to pi is where it normally is. So here's 0, here's pi. We can see that's in the same placement on the graph, so that distance is still our regular pi. Over on these ones, same thing. Here to here, visually we can see is 2 pi, but you can also go 0 to 2 pi and just make sure it's the same place on the curve. Okay, so here, 0 to 2 pi, same place on the curve. So our period hasn't changed. Okay, for these graphs specifically, for sine and cosine, we'd also want to check the amplitude. Okay, those ones are still from the midline or maximum, midline to maximum or midline to minimum, and those are still 1. Okay, so no scale changes were happening here, but we will put them together starting next time. Okay, I'm going to have you pause the video one more time for this matching. Okay, so 9 through 11, I want you to match each graph with its equation. Pause the video and do that for me. Okay, hopefully we got to where we could narrow some of these down. Okay, A and D are the only ones with vertical shifts, so they have a k value. Okay, and so the only graph that could have gone with, or equation, is 11. And we went with D since this did not have any other sort of shift, it was just sine. And then between these two, our feature, the midline, where it goes up afterwards, this one was shifted to the right, so I need a minus. This one was shifted to the left, I need a plus. Okay. Last thing we're going to do is look at graphing some things and start talking about some applications. Okay, so to graph these, I really am going to encourage you to think about the parent function. And again, sketch a little baby graph if it helps you. Okay, this one, cosine, starts at its maximum. And then it goes down, down again, back up, back up. So we're going to do these two things. This says go to the right pi, and this says go down 2. So from my original point, okay, let's put a scale on here. From my original point of 0, 1, we're going to run it through those two things. We're going to go to the right pi, and then we're going to go down 2. And then we're just going to follow the pattern on here. Because there was no scale change, it's going to go down the amplitude 1, and then down the amplitude 1 again, every pi over 2 this distance. Okay, so we're going to go down and over, and then down and over again. Okay, on the other side, we're going to mimic that, go in the other direction. So down and down. Once we're at that minimum value, the only option we have is to go up. So we're going to alternate now, going upwards twice, then downwards twice. Okay, this one, just like last time, is having us just go from negative 2 pi to 2 pi, so I'm not going to put arrows on here. It does not bother me if you add them on, as long as we don't have your arrows go past this way. They'd have to curve back up. But then it asks us to label the maximum and the minimum points. So that's just the ordered pairs on the graph. So here, this is negative 2 pi, negative 3, negative pi, negative 1, 0, negative 3, pi, negative 1, and 2 pi, negative 3. Okay. And I want to talk a minute about those max and min. So go up here for me. Okay. Our maximum and minimum points come from positive and negative version of the amplitude. And our amplitude was not changed here. So it starts at negative 1 and positive 1. But then we've got this vertical shift that affects both of them. So both of those need to go down 2. So this minimum would go to negative 3, and the maximum would go to negative 1. And that'll kind of help you check to make sure you're cycling between the correct two values to know what you're alternating between. Instead of 1, 0, negative 1, it's going to be negative 3, negative 2, negative 1, and back and forth through those values. Okay, so finding those before you start graphing may be helpful. Okay, so I want you to pause the video and try number 13. Okay, we will do 14 together since it's tangent. So this one, same concept, except we're dealing with the parent function of sine. So I'm starting at 0, 0, the midline, and then I'm going left pi, and then up 1. And for sine, when we think about the pattern, it goes up, down, down, up. Okay, so I'm going up, then down, down, up, and then continuing that pattern. Okay, this one it says label the intercepts. So we've got negative 3 pi over 2, 0. We've got 0, 1 for our y-intercept. And then we've got pi over 2, 0. So it wasn't asking where are my new midline values. It's literally asking for the intercepts here. All right, let's talk tangent. So this is another one where we've got a weird fraction, but we want to think about what it is as a decimal. So we've got 1/6 pi, and we know it falls somewhere between this 0 and 1/2, okay, going to the right. But we want to know where. So this is 0.16 repeating, and we know this 1/2 is 0.5. So this one's going to be really close to 0 comparatively to the last one. Okay, so about over here, and then we think about our parent function. So we've got 0, asymptote, 0, asymptote, and so on. Okay, so let's start off with our first point, which was 0, 0, and we're shifting over that small little chunk. And then our next important point is the asymptote. It's normally at pi over 2, shifting it over that same amount. And alternating between those two things all the way through the graph. Same thing on the other side. Make sure you're still going to the right of all these values. Okay, and over here, okay, if you're technically going to 2 pi, and this is strange, so you wouldn't necessarily have to do this for me, but it would stop somewhere randomly floating in space and then go. Okay, on your homework, I just have you complete, it says 2 cycles, like our first example did. So you wouldn't have to do all of these, you'd just pick 2 zeros and then 3 asymptotes to be able to do your 2 cycles. Okay, so this one doesn't quite make it and float somewhere there. But that would go from negative 2 pi to 2 pi, stopping just in the middle of the curve. Again, don't worry about this because on your homework I just have you sketch a couple cycles. Okay, but this one wants us to label the asymptotes, and that's where it gets a little bit weird, but it's going to help us because we want to be able to talk about domain and range with these graphs that have been transformed, and this is going to be one where it's not where it usually is. Okay, so our first asymptote is not at where it usually is because it's not at pi over 2. Instead, it's been shifted over that pi over 6. So we're going to find that math by taking 1/2 pi and adding 1/6 pi. Okay, and for this you'd need a common denominator, but if you're not good with fractions, please just toss those in your calculator and change it to a fraction. Just leave the pi part out. Okay, so this is 3/6 plus 1/6, and then we're tacking on a pi. 4/6 goes to 2/3. So this first one is x equals 2/3 pi. And then that's the only one we have to do by hand because all the other ones just occur pi later. So this goes back to what we practiced last time. Think of it as, instead of pi, as 3/3 pi. So we're adding 3/3 pi to get 5/3. Over here we're subtracting 3/3. So we have negative 1/3 pi. And then subtracting 3/3 again, negative 4/3 pi. Okay. And again, I usually won't have you do that many, but it's important to know where the first one is and where they occur after that. Okay. All right, now what I'm going to have you do is look at an application. This is just one of the many things we'll look at that we can model using a sine or a cosine wave. Okay, so what I'm going to have you do here is read through this information. I want you to answer questions A through C. We will talk about D together. Okay, so pause the video and try those 3 for me. Okay, so here we want to know what all these pieces basically represent. So there was no H value. K is this 6.5. And I started with those because that's what we were talking about today. Okay, but if we go back to last time, the things that affect the period and the amplitude can be found inside. Okay, remember the amplitude is just the value out front, so it's 0.8. And the period you find by taking the normal period, so our normal period for cosine is 2 pi, and then multiplying it by the reciprocal of the thing you see in here, which was 6 over pi. Pi's cancel, and we're left with 12. It's not uncommon for us to see an application problem that has pi in the equation because that allows us to talk about a period that does not have one. And why that's important for us is because all of these values that we just listed have context, and we're going to add them now. So our t, or our x value items, are going to refer to time in hours. So our period will be 12 hours. And our h value, if we had it, okay, if we had a translation, it would refer to hours. And then our vertical items, okay, our amplitude and our k, they're going to go with our y values, and that's going to talk about our height in meters. So this is 0.8 meters and 6.5 meters. So if we want to find the minimum height, we're going to go back to what we did over here, is we're going to talk about what our old max and min are based on the amplitude, and then apply the translation, the vertical shift. So we only care about the minimum, which means we would take this midline basically and go lower by that number. So negative 0.8 plus our shift. And that gives us 5.7 meters for our minimum height of this tide. Okay? And why I wanted to wait to have you look at D is because this one's a little bit harder to think about without using our calculator, but I want to talk about how we can do it algebraically for today, and then we'll bring out our calculator in the coming lessons. So here, thinking about our parent function and knowing that I only care about what time. So I only care about the x-axis. It doesn't matter what's happening with y, other than we're looking at the low points. Is I'm going to sketch this parent function, but only focus on the changes dealing with the x-axis. Okay, so my parent function is cosine, and there was no translation, so I can still start at the maximum and then swoop up to the next maximum. But what I need to label here is only the x value items, and because there was no translation, that means I just have to know what this end point is, what the period is. And that was 12 hours. So if we want to know what times during the 24 hours does the minimum occur, we just need to figure out where this is related to this 12. Okay, and visually that's the halfway point. So it'd be 6 hours. But it says during 24 hours, so we want to do this cycle again. So if this is 24, we need to know what this is. Okay, but if you recall, we know that every time the period completes, we hit another maximum or another minimum. All we have to do to get the next one is add 12 and know that our next one happens at 18 hours. Okay. Your homework for today has a staple, but it shouldn't take you too awfully long. If you struggle with any of the graphs or the couple of word problems that are on there, please, please, please come see me.